Stanford University.
We'll move on and talk about cosmology and what string theory has to offer cosmology. I suppose I could spend 2 minutes just telling you what I think the accomplishments and the failures of string theory have been. I think we'll do that another time. It's getting late, and we want to get on with some substance. All right, let's go back to the special theory of relativity for a moment, and just remember what it's all about. It's about thinking of space and time as a single entity that we call space-time. And space-time has a geometry. The geometry is described by a metric. I think I better leave it on. It's described by a metric tensor. Special relativity, in special relativity, the metric is especially simple. And the metric is just, if we take 2 points in space and time, 2 neighboring points in space and time, can you see them? No. It doesn't matter. But let's take 2 points in space and time, any 2 points in space and time. They're separated, let's call this the x-axis, let's call this the t-axis. And there's 2 more axes coming out of the blackboard. These are 2 arbitrary but neighboring points, and they're separated by some dx, dt, dy, dz. Separation here. And we define a new concept. The new concept is the relativistic distance between them, the proper time, and the proper time is defined to be dt squared minus 1 over the speed of light squared, dx squared plus dy squared plus dz squared. Different than you might have written down if this were ordinary Euclidean 4-dimensional space. If it were Euclidean 4-dimensional space, you probably would have put a plus sign here. You certainly would have put a plus sign there. And you might have left out the 1 over c squared. Although the 1 over c squared is just a rather arbitrary factor, you could always get rid of it by rescaling the space dimensions or the time dimensions appropriately. In other words, by choosing units for space and time in which the velocity of light is 1. You can always do that. Let's leave it for a moment. This is the proper time between 2 points along a trajectory. It's a nice concept as long as dt is bigger than dx squared plus dy squared plus dz squared. The proper time, the square of the proper time in particular, ought to be a positive thing. But notice that if dx squared plus dy squared plus dz squared is bigger than dt squared, something bad happens to this expression, namely d tau squared is negative. But never mind. Nevertheless, this is the definition of proper time between any 2 points. The most important thing for us tonight is how light rays move. How do light rays move? Let's suppose a light ray passes through those 2 points. Then the rule for a light wave, let's forget the x, the y squared and dz squared for a moment. Let's just take the x squared here. So the light ray is moving along the x-axis. Little infinitesimal separations along the light ray have only a dx and a dt. The rule about light rays is that along the trajectory of a light ray, the proper time is 0. Somebody traveling with a light ray, if you could, which you can't, would discover that the clock stands still, which is another way of saying that the proper time along the trajectory of a light wave is 0. So if you want to know what kind of trajectory a light ray consists of, you simply set the right-hand side of this equal to 0. So this is equal to 0 for the trajectory of a light ray. And another way to say the same thing is that dt squared, well, All right, c squared dt squared is equal to dx squared. I've just multiplied by c squared and that transposed one side to the right. Or taking the square root, it says that c dt is equal to dx. Or, what's the other possibility? Or c dt is minus dx. This is just another way of saying that a light wave moves with the speed of light. That dx by dt, that's the velocity of the light ray, is equal to c, or dx by dt is minus c. One of the light rays with the plus sign moves to the right. The other light ray with the minus sign here moves to the left. All right, the main point here is just that the way you diagnose a geometry like this to find out how light rays move is you solve the equation that says that the proper time along the light trajectory is 0. All right, now we're going to come to the more complicated geometries of general relativity. In general relativity, the metric is more complicated. It varies from place to place. The geometry varies from place to place. And it's described by a more complicated object, the metric tensor, which itself can vary from place to place. And we've done these things before, so I assume you know a little bit about it. You have a metric tensor, gi, well, let's call it g mu nu. Just remember our notation. Mu and nu are variables which run over the 4 dimensions of space-time. Usually we take them to go from 0 to 3. 0 being time, and x1, x2, x3 being the ordinary components of space. ds squared is g mu nu times dx mu dx nu. X mu and x nu are the 4 coordinates of space-time. And as always, in an expression like this, it is automatic that we sum over the repeated index. Here there are 2 repeated indices. So this stands for things like g naught naught d t squared, x naught is t, plus g naught 1 dt dx, blah, 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 all possible combinations with their metric coefficients. Again, if we want to know how a light ray moves, we simply, in other words, if we want to find the little infinitesimal gaps that correspond to a light ray moving from one to the other, we set this equal to 0. That's the rule. We set that equal to 0, and that gives us constraints on the allowable trajectories of light rays. That's the content, incidentally, of saying that light rays move with the speed of light. Whether the speed of light is 1 or c, or if you use some other units, something else, d, that doesn't matter. The invariant statement is that light rays move on trajectories of 0. This should be d tau squared, excuse me. Trajectories which correspond to 0 proper time. All right, now what we're going to do is we're going to examine a particular metric. It's the metric of a black hole. We're not going to solve Einstein's equations. We're just going to write down the answer. And we're going to inspect it for a while and learn about it. Tonight, I'm going to only spend a few minutes with the metric, showing you basically one property about the way light rays move in that metric. But we're going to get right to the point tonight about the quantum mechanics of black holes. The quantum mechanics of black holes is very strange. In some ways it's very strange, and in some ways it's extremely ordinary. In fact, it's very strange how ordinary it is, given how bizarre black holes are as classical non-quantum mechanical entities. Okay, so let's write down, let's just explicitly write down the metric. First, let's write down the metric of flat space. I'm going to set, from here on in, I'm going to set the speed of light equal to 1. In that case, what I would write down for the metric of flat space would be dt squared minus dx squared plus dy squared plus minus dx squared minus dy squared minus dz squared. All right, let's write it. Minus dy squared minus dz squared. Or this way. Now this here is nothing but the ordinary metric of ordinary flat Euclidean space here. And we can write it another way. We can write it in polar coordinates. Let's think about polar coordinates for a moment. Polar coordinates are the coordinates that I would use if I'm standing in the center, which I am. I'm always at the center. I'm very self-centered. All right? And I'm always at the center. And instead of using coordinates x, y, and z, I'm going to use coordinates which are the distance from me, r, let's call it r, the distance from me, and two angles to represent the direction that I might be examining. So an r and two angles. In fact, the two angles are often summarized by the symbol capital omega. That symbol actually stands for a unit sphere. A unit sphere, why a unit sphere? Because I can think of myself surrounded by a unit sphere, and then a point on the unit sphere determines the direction. The symbol omega often stands for a unit sphere, and the symbol d omega squared stands for the metric on the unit sphere. Maybe we should write down the metric on a unit sphere to just be really concrete. To represent the unit sphere, you need two angles. What are they called? Azimuthal and polar angles, or longitude and latitude. Okay? Two angles, theta and phi. And the metric of the unit sphere is the length element on the unit sphere is just d theta squared. Theta is the polar angle plus sine squared theta d phi squared. That's the metric on the unit sphere. Phi is the angle around the pole, and theta is the distance along an angular distance from, let's say, from the North Pole. Or maybe it's no, I think this is actually the distance from the equator. And this is the thing that's usually called, just abbreviated. It's just an abbreviation. It's called d omega squared. And it means the metric of a two-dimensional, ordinary two-dimensional sphere, but of unit length. If the sphere had some other unit radius, if the sphere had some other radius, then the metric of it would simply have the square of the radius multiplying the whole thing. But we're going to be drawing a unit sphere. Yeah, okay, let's put in what happens if the radius of the sphere is not 1. If the radius of the sphere is not 1, then we would write r squared, where r is the radius of that sphere, times d omega t theta squared plus sine squared theta, d phi squared, or just r squared d omega squared. Okay, so r squared d omega squared is the metric of a sphere of radius r. Now I stand at the center and I look around me, and I see 2 points. They're separated. You could think of them as separated by a dx and a dy and a z, but no, I'm going to think of them as separated by a dr, a d theta, and a d phi. Okay? Dr, different distance to me, different angle, and so forth. What's the distance between those two neighboring points? The distance between those neighboring points in ordinary flat conventional space, in other words, the thing which really replaces this thing, this piece of it, in polar coordinates, it is dr squared plus, that's the difference in radial distance along the radial distance, and then a contribution coming from the distance in angular space, and that's just this, plus r squared d omega squared. Schwarzschild, S-H-I-L-D. Yes, yeah.
So there is
S?
the question would
Not
be
shield, but shield.
whether there's a T or not, and there is.
No T. D. No, no T.
No T.
Okay.
No, I mean in the middle before
the Z.
Before the Z, yeah.
Oh, no, I don't think so. It's Schwarzschild. Schwarzschild, yeah. There isn't. Okay. How does this get modified in the presence of a black hole? Here's a black hole. Some coordinates. And we're going to describe the metric again in polar coordinates. It's a nice round object. Nice spherically symmetric object. Polar coordinates are the convenient coordinates to write it in terms of. In fact, that's generally true. When you have something which has nice spherical symmetry, then polar coordinates are usually the best coordinates to describe it in. Okay, so how do we do? First of all, if we go very far from the black hole, the influence of the black hole should be should fade as you move away. That's the first thing. That means that far from the black hole, this should be pretty good. All right, I'll write down the answer and then we'll just check that. The answer is 1 minus. Now, a black hole has a mass. Let me just write down over here what variables are interesting. There's the mass of the black hole, m. There is something that we'll call either the Schwarzschild radius or the radius of the horizon. All right. We can call it r sub s. That's for Schwarzschild, or Schwarzschild. And that happens to be related to m is twice mg. And just once I will put the speeds of light in. After that, we'll set the speed of light equal to 1. C squared. I may here and there decide to put the c's back in just for illustrative purposes. But if I write that r Schwarzschild is 2mg, you know that I'm setting the speed of light equal to 1. All right, so it's 2mg over c squared little r. Now, little r is the radial coordinate. Little r is the radial coordinate. We can, in brackets, we could also write this as 1 minus r Schwarzschild over r, the ratio of the distance to the point where the r, little r here is the point of interest. R Schwarzschild is the radius of the horizon. We're interested in points far from the black hole for a moment, or at least out beyond the horizon of the black hole. So little r is bigger than big R here. All right, that gets multiplied by dt squared, replacing this. Now this looks good. When little r gets big and we go far from the black hole, this here becomes small, and we just get back r1 dt squared. Then there's minus, the same thing except in the denominator, 1 minus 2mg over c squared r times the r squared. Again, when little r gets large, the denominator becomes 1, and this just becomes the r squared. And then the last term here, that's easy, just plus r squared the omega squared. This is the metric of a Schwarzschild black hole. Memorize it. It's a great thing for cocktail parties and, you know.
Last term has a minus sign also.
Yeah, thank you. Good. Good for you. All right, and 2mg over c squared is just r Schwarzschild. Oh, did the mic fall off? Okay. Okay. All right, so let's erase off the blackboard what we don't need. Now, when you look at this, you see something a little bit strange. 1 minus 2mg, if little r is large, this is small, And what's in here not only is close to 1, but even more important, it's positive. What's here is also positive. So we haven't done anything really weird like changing signs of coefficients and so forth. But notice that something unusual does happen at the point where r gets small enough that this gets bigger than 1. Where does that happen? That happens, you know what, from here on, I'm going to get rid of the c squares. They're only going to confuse me. I'm going to forget about them. Just let's get rid of them. Set c equal to 1. Where is the crossover where this gets bigger than this? And that happens when r is equal to 2mg. Something happens when r, or when 2mg over r is equal to 1, same thing. When r becomes smaller than this, you're inside the black hole. You're inside the Schwarzschild radius. At r equals to 2mg, something really weird happens. The coefficient of dt squared becomes 0. Sounds like no time. No time. When the coefficient here is 0, the proper time from one value of time to a neighboring value of time is just 0. All right? And even worse, the coefficient of dr squared gets infinite. It sounds like something rather dramatic happens at the horizon or at the Schwarzschild radius of the black hole. And we're going to come back to that. We're not going to analyze that tonight. Tonight, we'll just take this metric and say, all right, something interesting is happening at r equals 2mg. But there's another place where something interesting is happening. I don't know, interesting, weird. And that's at r equals 0. At r equals 0, not only is this negative, but it's also infinite. Likewise, this thing has some nasty behavior in it. So at r equals 0, some kind of singular behavior happens, and at r equals 2mg, some kind of other kind of singular behavior happens. They're quite different. They're extremely different. They have very little relationship to each other. I can tell you right now what the difference is. If you were falling into a black hole, well, whenever you're falling into a gravitational object, you experience tidal forces. Everybody know what tidal forces are? Anybody not know what tidal forces are? Okay. You experience tidal forces. And if you're big enough, the gradient of the gravitational field pulls on you differently in different parts of your body. Your feet are pulled harder than your head, so you get stretched. You're also squeezed inward to some extent. Those are called tidal forces, and you can feel them. Of course, you wouldn't feel them jumping off a diving board because you're too small by comparison with the scale over which the gravitational field of the Earth changes. But if you fell into a black hole, you would feel a tidal force. The tidal force at the horizon is finite, and as the black hole gets bigger and bigger and bigger, the tidal force at the horizon gets less and less and less. So nothing dramatic would happen. You wouldn't get squeezed. If there's a sufficiently big black hole, you don't get squished at the horizon of a black hole. And we're going to work that out. We're going to see that. You don't get squeezed like toothpaste into the black hole. Perfectly benign place to fall into, as we will see, even though the mathematics looks like something fairly bad happens. On the other hand, at r equals 0, that's where you would really feel pain. That's where the tidal forces become infinite. That's where all hell breaks loose, and the nasty place. R equals 0 is called the singularity. R equals 2mg is called the horizon. Okay, let's talk about light rays now. Let's talk about a light ray moving radially outward at some angle on the sphere. In other words, maybe along the north pole of the sphere, or the east pole of the sphere, or the south pole of the sphere, some pole of the sphere, some direction on the sphere. The light ray is moving radially outward. That means along the light ray, there is no change of the angles. The angle, as I shoot the light ray out, the angle is constant that it's moving in. And so along the light ray, d omega squared is 0. dt is not 0 along the light ray. As you move from one point on the light ray to the next, time changes a little bit. Not proper time, but ordinary time. And also the radial distance changes. So you're watching the light ray, you have your clock, you see a little bit of dt and a little bit of dr. How does the light ray move? What's the equation, what's the rule for the light ray? The rule for the light ray is that along the light ray, the proper time is 0. So let's work that out. That's 1 minus 2mg dt squared must equal, I'm setting, this we don't need to worry about. I'm setting the rest of it equal to 0, and I'm doing that by setting the dt squared equal to the dr squared term. Equals 1 divided by 1 minus 2mg over r dr squared. That's the motion of a light ray. We can multiply both sides of the equation by the thing in the denominator here, and that just squares this and removes this. And now I can take the square root if I like. It just says that dr, the distance along the radial direction that it moves, is equal to 1 minus 2mg over r dt. If you're far away from the black hole, this is close to 1, and it just says dr is equal to dt. Of course, if I put the speed of light back in, there would be a speed of light here, and it would say that dr is equal to c dt. But that's just a statement that the light ray moves with the speed of light. In fact, the whole statement is really the statement that the light ray moves with the speed of light. But you can see that as you move in closer to the black hole, the mathematical description of the motion of the light ray gets modified a little bit. And in fact, let's divide by dt. Let's divide by dt. Oh, incidentally, I did take a square root, didn't I? Yeah, so that means there are two possible solutions. One corresponds to an outgoing light ray, and the other corresponds to an infalling light ray. Those are the two branches of the solution, but let's take the outgoing light ray. And if you want the ingoing light ray, you just change the sign. Okay. This, of course, is the time rate of change of the radial coordinate. We could call it the velocity. We could call it the velocity in the particular coordinates that we're using. The r dt, that's the rate of change of the radial coordinate with time, and that's equal to 1 minus 2mg over r. As I said, far away, nothing unusual. But what happens when you get in very, very near the, let's not worry about the singularity tonight. Let's only worry about the horizon. At the horizon, 1 minus 2mg over r goes to 0. R becomes equal to 2mg at the horizon, and 1 minus 1 is 0. So very close to the horizon, the light rays slow down. They slow down. The closer you get to the horizon, the slower they move outward. And right at the horizon, the light rays don't move at all. They just sit there, static, and they don't move at all. So we could draw a picture of this. Let's draw time. Here's time. Let's draw r this way. And at some value of r, namely r equals 2mg, let's put that in over here. That's the horizon of the black hole. Okay. That's the horizon of the black hole. And now what happens to, let's take outgoing light rays. When we're far away, dr by dt is close to 1. That means the light ray on this diagram moves with close to the 45-degree axis here. But what happens as we get closer to the black hole? As we get closer to the black hole, the light rays move much more slowly. In a given amount of time, they move a smaller distance. Being upright here means moving slowly. And as you get very close to the horizon, the light rays hardly move at all. And right on the horizon, the light rays just stand still. Or the light rays that are trying to get out just stand still. Okay? So they don't get out. Anything that's inside the horizon, we haven't analyzed it in detail, but let me tell you what happens inside the horizon. Inside the horizon, all light rays, whether you think they're directed outward or not, you're falling into the black hole. You try to send a light ray out or you try to send a light ray in, exactly, well, not exactly the same thing, but in either case, the light rays fall inward. Right to r equals 0, where r equals 0 is where the singularity is. Light rays that originate inside the black hole simply cannot escape. Light rays that originate close to the horizon take a very, very, very long time to escape. Light rays right on the horizon just sit there, and light rays far away do what light rays do if there was no black hole there. Okay, so that's the basic framework of the Schwarzschild black hole. That's really all there is to it. There's, of course, a lot more to it. And we're going to do a lot more, but not.
Could you clarify the statement that light slows down and what exactly?
Yeah.
Is there more to it than just that statement? I thought the speed of light was invariant.
That's R and that's T.
Yeah, I understand that.
Yeah. The rule that light rays move with the speed of light depends on what is the speed of light? 3 times 10 to the 8th something. But if I change from centimeters to meters or meters to centimeters, it becomes 3 times 10 to the 10th, or meters to kilometers, it becomes 3 times 10 to the 5th. What's going on here is effectively, as you move in toward the black hole, there's kind of a moving change of units. R is being measured in different units at different places. But the real point is there's a universal statement about the speed of light, and it's that along a light ray, the proper time is 0. That is what replaces the statement that the speed of light is 3 times 10 to the 8th meters per second for all speeds of light. All light rays move the same way. They move on what we call a null trajectory. A null trajectory means that the proper time along the trajectory is exactly 0. That's the universal statement for all light rays, which is, in special relativity, becomes the statement that they all move with the speed of light.
And that stands true for regardless of the medium that it's traveling?
No.
No,
That's in a vacuum. Right.
Could you draw an incoming light ray again on the right there?
Yeah, okay. First of all, I drew an outgoing light ray, and an outgoing light ray just sort of started very close to the horizon here. It sticks. It doesn't want to go anywhere, and then eventually it goes off. The incoming light ray does just exactly the opposite. It starts to fall in, and then asymptotically gets closer and closer to the horizon, never quite getting there. So one lesson is that even a light ray that's shined in toward the horizon takes an infinite amount of this kind of time here, what's called coordinate time. It takes an infinite amount of coordinate time to get to the horizon because of the slowdown effect. Okay, so we have now the basic setup. And I actually want to jump from the geometry of a black hole, which we're going to come back to. It's very interesting, and many things to explore about it. In particular, the most interesting of which is to explore the nature of the horizon. What kind of thing is the horizon? What kind of funny kind of thing is going on at the horizon? Is anything funny going on at the horizon? We are going to explore that. We're going to explore the question, how do you make a black hole? But we'll come back to this later. What I wanted to really jump into for tonight, and maybe for next time, is the quantum mechanics of black holes. Black holes are objects. Now, the question is, are they objects like any other kind of object, or are they something new and special which violates the laws of physics? I'll remind you what Professor Hawking said about black holes. He made a claim, and the claim was a very well-reasoned claim, an extremely well-reasoned claim. He said that anything that falls onto the surface of a black hole, he said anything that falls into a black hole. We will come to the question of whether things do or don't fall into black holes. Looks from this point of view that it takes an infinite amount of time to fall into the black hole. This is a contentious question that, it's not contentious, it's a subtle question that we'll come back to. But for the moment, let's just think about things which fall onto the horizon of a black hole in this sense here. They get closer and closer and closer to the horizon. And they sort of get stuck on the horizon from the point of view of outside. They don't get back out. If they don't get back out, that means that all the information that they brought into the black hole is lost to the outside observer in the form of either, depending on, we'll discuss it later, but depending on whether you envision it as falling into the black hole or just progressively closer and closer to the horizon of the black hole, it becomes unavailable to the outside. All right, that's not such a bad thing. You just say, well, okay, but the information of what fell in is simply getting closer and closer to the horizon. No big deal. It's it hasn't disappeared, it hasn't gone anywhere, it's just gotten squeezed tighter and tighter onto the horizon. The problem is, as we're going to see tonight, or tonight and partly next time, there's reason, not a reason, it's extremely, well, there's complete consensus about it. Black holes in time evaporate. If black holes in time evaporate, then the question is what happened to all the little itsy-bitsy bits of information, or whatever it is that fell onto the horizon. Does it just disappear out of this world? Or is it somehow stored inside a little tiny remnant of the black hole that refuses to disappear? Or does it get radiated out with the evaporation products? Exactly what happens. This was a big puzzle in physics. But before we can address the puzzle, and it was string theory in part which largely resolved this, before we do that, we have to understand why people thought that why people think that black holes evaporate. Now, a black hole is the most dull object in the universe. If you create the black hole and leave it for a while, it settles down to a perfectly spherical, totally uninteresting object. Nothing comes out of it. It's totally black in the sense that, no light comes out of it, and it's very uninteresting. You can't get messages out of it or anything else. But it turns out not to be quite true. Black holes are not as dead. Let's call them dead. Dead in the sense that they are infinitely cold, infinitely, what should we say? Infinitely black. Black has two meanings, incidentally. Black can either refer to, emits no light at all, or it can refer to the idea that it emits black body radiation. Black body radiation is thermal radiation, heat radiation. So let me just, black holes are black in the sense that they emit heat radiation. It was thought earlier that black holes were black in the sense that they emitted no radiation. So we need to come to an understanding of what it was that made Hawking, Bekenstein, other people think that black holes have some heat in them. They're not completely dead. They have some heat, and because they have some heat, they glow. Because they glow, they give off light. Because they give off light or radiation, they give off energy. That means with time, their energy must decrease. Well, energy and mass are the same thing, E equals mc squared. And so with time, the mass should decrease as it gives off this radiation. And if the mass decreases, then the Schwarzschild radius, 2mg, decreases. And one should expect in time, if black holes really do have some active heat in them, that eventually they will simply disappear because they'll radiate away all their energy. And if that happens, as I said, there's the puzzle of what happened to everything that fell in, basically. Okay. To understand, and we're not going to do any fancy mathematics of studying quantum field theory in the background of a black hole. To really understand the concepts, you don't have to. And I don't feel up to teaching an advanced course in quantum field theory in curved space tonight. It would take more than one night. So we're going to do something simpler. We're going to go through Bekenstein's arguments about why black holes have to have entropy. Now first, before we talk about why black holes have entropy, let's talk about entropy in general. What is entropy, and how do you define it? We can define it either with precision or we can define it qualitatively. I prefer to define it qualitatively. To understand what entropy is, you need to understand what information is. And let me be very, very simplistic about what information is. Information, the information about a system. The information about a system, let's not ask about what it is, but how do you quantify it? How much information is there in a system? Or better yet, how much information separates one system from another? What's the way you explain to somebody the difference between systems? Well, you ask a bunch of questions about the system. I'm not even going to try to ask the question. Well, yeah, we could. Here's a system. Here's a system. It's a big box. The box is broken up into little boxes. Those little boxes are about as big as an atom. And you can know everything about what's in this box if I tell you yes or no whether there's an atom. I would have to tell you what kind of atom, but let's simplify it. Let there be just one kind of atom in the world. And either a box is empty or a box is full. If I go through the boxes and tell you whether there's an atom there or not, I have told you just about everything about that box. There's an atom here, 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 here. No other atoms. Well, then there's a block or a lump of stuff in the middle. Okay? Maybe that one's missing. Now it's a lump of stuff with a funny shape. So you can go through this thing with a bunch of yes-no questions. Is there or isn't there an atom in this box, that box, and so forth? Another way of describing information is to say, if I want to describe the system, what I need to do is give a code to describe it. And the code might simply be a series of zeros and ones, where you go through this thing, 0, 0, 0, 1, 0, 1, 1, 0. In other words, it could be a long binary digit. How long? Well, it depends on how many bits of information you're trying to describe, how many yes-no questions it takes to describe a system completely. The number of yes-no questions, or the number of binary digits that you would have to prescribe to describe a system or to distinguish it from other systems, is called the information in the system. Information theorists use it all the time, and as I say, they characterize it in terms of bits. A bit is a yes-no question. Okay? And, okay, so the quantity of information is characterized by the number of bits. In this system here, the number of bits would just be the number of boxes. The number of boxes where you might or might not have a, an atom. That's pretty clear. I mean, we could describe everything in this room by breaking it up into sufficiently small boxes. If we didn't want to deal with the fact that there are different kinds of elements, we could break it up into even smaller boxes and simply ask whether they're, well, I suppose we would have to distinguish electrons from quarks. But we could always break it down into yes-no questions. Is there a quark in this box? Isn't there a quark in this box? Is there an electron in this box? Isn't there an electron in this box? And eventually, we would learn everything there is to know about this room by asking that series of questions. The minimum number that it would take to describe the room and to distinguish it from every other room would be the quantity of information that describes that room. Yeah.
But that's in a static situation. In other words,
No, it could be an instantaneous description. Yeah, yeah, yeah. At a moment of time. At a moment of time. Right, right. Another fact: information never disappears. This is a basic idea in physics. It's probably more basic than anything else. And the meaning of that is the following: that if you start with two different configurations, let's say here's one, here's another one, they're fairly similar, as a matter of fact. They just have a couple of atoms out of place. But they're different. They're distinct. They're distinguishable, distinct, and then you can do an experiment in principle to tell the difference between them. Then if you let them run means let them evolve with time, they will stay different. Of course, they will change relative to what they started with. This one might move to here, this one might move to here, and so forth. But if you start with two distinctly different configurations, they stay different. Okay? They don't run into each other. For example, you never have a situation where as you run these things, they will evolve to the same configuration. That's a very, very big, that's such a deep rule of physics that people forget to state it when they're stating what the laws of physics are. That the amount of information that it takes to describe a system is constant in time, and that the distinctions between systems never disappear. Okay, now, sometimes it looks like information disappears. You drop a series of water molecules into your bathtub, and you might drip them in some very, very specific way. You might drip the drops of water in with Morse code messages on them, two different bathtubs full of water. And one of the messages, I don't know, some great literary masterpiece, and the other one, some other great literary masterpiece being coded in the dripping of the faucet. And those two bathtubs full of water started out differently. Okay? They sure look the same after a few minutes. After a few minutes, you let that water settle down, and they sure look the same. But that's only because you don't look carefully enough. If you could look carefully enough at every single molecule in those bathtubs, you would find that the configurations of them stay the same. We might say that effectively information doesn't disappear, but it gets hidden. It gets hidden because it gets hidden by the fact that there are just so many degrees of freedom, and they're so small that you can't see them, that in effect, information which is there is effectively lost just because it's stored in degrees of freedom which are too small and too numerous to keep track of. Okay? So in practice, in a sense, information does disappear, but not in principle. There's a notion of hidden information, information that's inaccessible to you for one reason or another. Now, of course, the notion of inaccessible can depend just on how good your ability to study and manipulate the system is. It might depend on how good your microscope it is. It might depend on how quick you are in your ability to measure molecules and so forth. But subject to whatever limitations there are, there's a notion of inaccessible or hidden information. What is entropy? The simplest statement of entropy is that it is the number of hidden bits of information, the number of things which in principle are there to distinguish things, but which are just unavailable to you because they're stored in things which are too small and too numerous to keep track of. So in the case of this bathtub full of water, so the only thing I really care about is how hot the bathtub is. I don't want to burn myself when I get in. I want to make sure there's enough water in the bathtub that I can take a nice bath. I want to, what else? I want to make sure it's water, not hydrochloric acid. But you know, there's a handful of things that I want to know about that water, and furthermore, there's a handful of things that I can know about the water. The amount of energy that's in it, that's in the form of its thermal energy, the fact that it's water, and a few other things. And that's a pretty much complete description of the water. Well, the water might have ripples on it. I don't care much about the ripples when I'm taking a bath, but nevertheless, I could see the ripples and I could distinguish the fact that the bathtub was filled up 5 minutes ago than half an hour ago. But if you wait a while, even those ripples go away, and there's not even any ripples on the surface to tell you any detailed information. It's all hidden in the microstructure of the molecules. So all that information is hidden information, and it's called the entropy. That's what entropy is, the number of bits of information which are unavailable. Now, there are more technical definitions, but for the moment, I think that that is good enough for us. Incidentally, entropy and energy are the basis for thermodynamics. Normally, when you learn thermodynamics or statistical mechanics, particular thermodynamics, you start with the idea of temperature. Temperature is a highly derived concept. Right? Well, you know, it's what you measure with a thermometer. Very simple. Yeah, what you measure with a thermometer is a very, very highly evolved thing. It's easy to measure, but it's very hard to define. The definition of temperature, what is the definition of temperature? Anybody know the definition of temperature? No, of course you don't, because the definition of temperature is a highly contrived thing. Not so much contrived, it's a what's the right way? A derived concept, derived from the ideas of entropy and temperature. Okay, so I'm going to tell you now, all right, we have energy. I assume we all know what energy is. And we have entropy. Now, let me give you an example. Entropy might be the amount of hidden information in the atmosphere. Okay. I'll tell you right now what temperature is. I have to write an equation first for myself, just so I get it right. Okay. Temperature is the change in entropy of a system if you add 1 bit of information to it. If you change, now here's an example. I'll give you an example of where this comes up. You take your computer. Your computer is full of bits of information. The bits are stored individually in the form of what? Bits. Yeah, I mean, whatever. Some little thing inside the computer is either switched on or switched off, and that's your yes or no question. Now, your computer is full of information that you put in there. Supposing I want to get rid of a bit of information. In other words, I want to eliminate some, I'm not going to eliminate the circuit, I just want to set it back to its original starting point. I want to take the computer and reboot it, just to get it back to its original starting configuration. In that case, I will lose a lot of information, all the information that's in the computer. Well, let's not go that far. let's just erase one bit of information. If you erase one bit of information, I just told you it's impossible to erase bits of information. That's a basic law of physics. What really happens is that bit of information, whatever it is displaced from inside the computer to out into the atmosphere. The distinction between one configuration of the computer and another configuration, which differ by one bit, that distinction gets taken from the computer into the atmosphere so that the atmosphere becomes a little bit different by one bit of information than it was before you erased the bit. That process of transferring a bit from the computer into the atmosphere heats the atmosphere, adds a little bit of energy to the atmosphere. It's an inevitable heating that happens because you erase bits from your computer. What is the energy that's transferred to the atmosphere when you transfer one bit? The answer is the temperature. That's the definition of temperature. The change in the energy of a system when you add one bit of information to it is called the temperature. Okay. You could write this another way. You could write the change in the energy when you change the number of bits, by some number, is the temperature times the change. Well, okay, let's slow down. Notation for entropy. We need a notation for entropy. I don't want to say entropy every time, and I don't want to write the word entropy on the blackboard in equations. We need a symbol for entropy. The standard symbol for entropy is S. S is entropy. Okay, now what I told you is that the change in the energy, let's call it delta E, when I add one bit, that means when delta S is equal to 1, if delta S is 1 unit, then the amount of energy that gets added to the system is called the temperature. What happens if you add 2 bits to the atmosphere? Then the energy of the atmosphere changes by twice the temperature. What happens if you add 3 bits? 3 times the temperature. What happens if you add S bits? Then the change in energy is T times the change in entropy. The change in energy is proportional to the number of bits that you transfer to the atmosphere or that you transfer to anything, a bathtub full of hot water. In other words, it's the change in the energy when you hide a certain number of bits of information. When you remove them from someplace and hide them in your whatever it is you're hiding them in your heat bath, basically. Okay. This is a basic formula of thermodynamics. Extremely confusing formula if you start with temperature as the basic concept. But it's a very simple concept if you start with entropy as the basic concept. Then temperature is, as I said, the energy that you add when you add 1 bit. And this is usually written differentially, dE equals TdS. This is one of the fundamental laws of thermodynamics. The change in energy is the temperature times the change in entropy. That's the definition of entropy. Hidden information, stuff that you can't easily see.
Can I add? I did a calculation comparing a change in entropy of a hard drive if you erased it 100 gigabytes and how much that temperature would be for a glass of water. It's about 10 to minus 15 degrees.
Ooh, is it that?
That's small of a change of temperature.
If you erase how much?
About 100 gigabytes of information from a hard drive.
Yeah, it's very simple. Yeah, a bit of information at an ordinary room temperature. Room temperature is very low for one thing. Yeah, at room temperature, right. So room temperature in any kind of reasonable other units is very small. And yeah, a bit is typically a very small amount of energy at the ordinary temperatures. Right.
Are you using the computer hard drive as an analogy, or are you
No.
actually saying?
No. That's a real fundamental law of computers. That's Landauer's rule about erasure of information.
Because when you erase a bit of information on a hard drive, you're not actually erasing anything. The bit's still there. You're just setting it from a higher voltage to a
No. Erasing it means you haven't erased the object which held the bit. All right? But let's say here's what you're going to do. You're going to, whatever the configuration of the computer is, you're going to turn that bit to off. So you will have forgotten what was there because you turned it off. In that sense, you've erased the knowledge that little circuit had. And eventually, you could turn off by rebooting the computer or by starting the computer over and bringing it back to the configuration as when you bought it. There's nothing left in that computer that remembers what you did to it. So you've erased it. Right. You've erased it, and the number of bits that you've erased, in other words, the number that you brought back to neutral, is the change in the entropy of the computer. And that, or if you like, that's the number of bits that had to be taken from the computer, put into the atmosphere, and that's what you calculated when you calculated the.
The real thing is much more inefficient, so it wastes a whole lot more. Yeah. That's right. Right. You do a lot of other stuff besides erase the bit normally, like you rub your finger on the keyboard and all kinds of other useless stuff. Right.
Does that say that at high temperatures, hiding one bit of information
Costs more energy.
costs more?
Yes. Well, or right. We'll heat the system. We'll increase the energy of the heat bath by more. The higher the temperature, the more energy you will be putting in when you hide that bit. Yeah, that's exactly what it says. But in a sense, that's the definition of the temperature. So it's a question of horse before the cart or cart before the horse. Yeah.
If you write on top of a previously existing bit, and you have lost the information of what that bit was,
Yes.
that changes the entropy.
Yes. Yes. It changes the amount of information. It decreases the amount of information in the computer. But that information cannot disappear out of this world, so you wound up putting it into the atmosphere, but it's hidden in the atmosphere, and so it's entropy. Okay, that's the basic idea of entropy. Why my teacher didn't teach me that when I studied thermodynamics in 1959, I don't know. I went around asking my colleagues, when you teach statistical mechanics, do you teach that? And basically what I found out is none of my colleagues knew it. Not good. Hidden information, right? The computer scientists all know it.
But there were no computers back then.
Right. Yes. But these ideas, that's right. But these ideas go back to Boltzmann. These ideas are older than computer science. Actually, there was no, all right. In statistical mechanics and in physics, they go back to Boltzmann in the 19th century. In computer science, they go back to the 40s. Shannon, Claude Shannon was the one who formulated these ideas. Okay, enough history. Okay, so now let's talk about the information that's hidden in a black hole. As I said, you can either think of it as hidden in the black hole, or you can think about it as hidden on the surface of the black hole. You keep throwing stuff into the black hole, and it accumulates closer and closer to the horizon, in some sense, and becomes unavailable, gets all smushed up onto the horizon. It takes light forever and ever and ever to get out of the horizon, so it's effectively lost. Why did Bekenstein think that black holes had entropy? Well, I'm going to tell you the way I think about it, but it was also the way Bekenstein thought about it. But I'm going to tell you why he thought there was entropy by computing the entropy, by computing the amount of information that you can store in a black hole. What I'm going to do is imagine building up the black hole by throwing bits of information into it. And I want to know, after I have thrown in a certain number of bits of information, how big is the black hole? The logic is very, very similar to asking, how full will a bathtub be if I fill it by dropping in atom by atom, and I tell you after n atoms, how full will the bathtub be? Well, the way you figure it out is you say an atom has a certain volume. Every time you drop an atom in, it adds to the volume of the water, and each differential drop changes the volume by a little bit and raises the level of the water by a certain amount. So if you want to know how high the water will be for a given number of drops, what do? You just count how much will the water be raised by dropping in one drop. Of course, you don't have to be that dumb. You could be smarter than that, but that would be one way to do it. Just drop by drop by drop, and discover each drop that you put in has a certain volume, therefore it will raise the water a certain amount. After n drops, the water has a certain height. We're going to do the same thing by dropping in bits of information to form a black hole. We can start with a small... Yeah.
How does throwing in photons, electrons, chairs relate to throwing in information?
Okay, so we're gonna come to that, but basically we're going to throw something in which we're pretty sure has no other information in it other than the question of whether it's there in there or not. In other words, we're going to fill this black hole up by a series of processes for which each one of them has no other information stored in it other than that a photon went into the black hole. You can simply ask, did the photon go in or didn't the photon go in? That's a yes or no question, and yeah.
You live in coordinate time, right? So it'll take an infinite amount of time for that information to get into the black hole.
But it doesn't take very long for it to get squashed onto the horizon where it becomes unavailable. Yeah, right. But, yeah, that's another example. Or the polarization of the photon. The polarization of the photon is it's either up or down along the x-axis, so it's one bit of information. But you have to be careful. And here's what you have to do. All right, so we're going to start. Let's take a black hole. There's a black hole. It has mass m. It has radius r, or the horizon has radius r, which is twice mg. We've already made it. We've got it there. Now we want to throw in one more object, and that should be the simplest possible kind of object for which we can simply ask, is it there or is it not there? One bit of information. Let's think of it as a photon. All right. But we have to be careful. If we throw in a photon from here, let's suppose this black hole is 1 kilometer in radius, and we throw in a photon along a beam of laser light where the photon has a wavelength which is some microscopic wavelength. Then there's a lot more information in that photon, in the arrival of that photon, than just whether it got in or not. For example, did it come in from here? Did it come in from here? Did it come in from here? In other words, the angle on the horizon where it arrived from. That's clearly going to, there may be a lot of bits of information in describing the angles to various amounts of precision. So throwing in a photon is not by any means necessarily the same as throwing in one bit of information. There's a lot more information. You know, you could begin a yes/no question as follows. Is it in the upper hemisphere that it came in? Yes. Okay. Is it in the upper half hemisphere to the right? Or no. Okay, it's to the left. And now imagine dividing up the horizon of the black hole and asking a series of yes/no questions until you've localized where that photon came in to the maximum degree that it can be localized. It can't be more localized than its wavelength. It's fuzzy out to its wavelength, but it's clear that there's a lot more yes/no questions you can ask about that photon coming in, and so that photon is not one bit of information. It's a lot of information. Unless you do something to that photon, or you deal with a photon which is so uncertain about where it is, because photons are always uncertain, they don't have any brain, but unless in principle there is an uncertainty in the sense of Heisenberg, unless there is a maximal amount of uncertainty about where that photon entered the black hole. Now, what does that mean in practice? In practice, that means that the wavelength of the photon is a measure of how delocalized the position of the photon is in quantum mechanics. We're talking about quantum mechanics now. If the wavelength of the photon is as big as the whole black hole, then when that photon arrives, it arrives in a way where there's complete uncertainty about where it entered from. So the first thing you want to do is you want to work with photons which have the longest possible wavelength but can still get into the black hole. Is there a restriction on not being able to get into the black hole? Yes. It's a fact that that's been known basically from classical physics, that if you shine light on a black hole of wavelength longer than the size of the black hole, it just reflects off. It will not go in. Only wavelengths which are no longer than the radius of the black hole horizon have any chance of penetrating through to the horizon. So what's the best you can do? You can work with photons whose wavelength is comparable to the radius of the black hole. They are so uncertain in their location that you can't tell where they entered the black hole. On the other hand, they're short enough wavelength that they can get into the black hole. So you're working just on the margin, on the edge, where the photon will go into the black hole, but where it will provide no other information other than it either got in or it didn't get in. Okay, so let's add a photon to this black hole.
Do you ever worry about which direction? I mean, it seems like that's more information.
Well, it really isn't if the wavelength is very long, because the wavelength is so long that the electric field is varying very slowly across the black hole. And it doesn't matter which direction it comes in from. But you're right to ask the question, but I think the answer is no, that if the wavelength is long enough that it doesn't provide any information. Okay, good. So we want to send in a photon of wavelength lambda equal to 2mg. Now, first question, what is the energy of such a photon? We're going to be adding some energy now. Here's this business that whenever you hide a piece of information, you wind up adding a little bit of energy to the system that you're hiding the information in. So how much energy have you hidden inside the black hole, or how much energy have you added to the black hole? The energy of the photon. All right, so we'll just write down a formula or two about energies of photon. I'll write down just to remind you. The energy of a photon, or any light wave, is equal to the speed of light times its momentum. P is the momentum of the photon. Now, what's the connection between momentum and wavelength? Anybody remember? H bar over lambda. H bar, Planck's famous constant. All right? This is, because we're dealing with photons, because in quantum mechanics information is quantized into photons, this is a real quantum problem. We're going to see where H bar winds up. It will be interesting to see where H bar winds up in this formula. All right, so what's the wavelength? The wavelength, or the momentum is H bar over lambda. Lambda being the wavelength. The shorter the wavelength, the higher the momentum. So now we can say that the energy of the photon that we threw in is the speed of light times Planck's constant divided by lambda.
Is it h bar over lambda or h bar over lambda bar, which is the same as h over lambda?
Oh, I'm not keeping track of 2 pi's. It's h bar over lambda, isn't it? No. Yeah, it's h bar over lambda. H over lambda? That's the energy is h over lambda? I can't remember. It is C times P. That's not important. I don't care about 2 pi's. Let's forget 2 pi's. Not important. Order of magnitude. Energy is CH over lambda. And yeah, P is H bar times the wave number, and there's a 2 pi. You're right, there's a 2 pi. Okay, but there's this H over lambda, not important, H over lambda. The energy is H over lambda. Now, lambda, we're going to be choosing equal to the size of the black hole. So now we can write down that the energy that we've put in, apart from factors of 2, I'm not interested in factors of 2 here, we can't, this calculation is not going to be that precise within a factor of 2. All right, so the energy that we're adding to the black hole is the speed of light times Planck's constant divided by m over g, and that adds 1 bit of information to the black hole. Now I could stop right here. I have now told you how much information it cost, how much energy it cost to hide 1 bit. What have I told you? The temperature. Here's the temperature of the black hole. CH over mg. That's the Hawking temperature. Now there are some factors of 4 and pi's and things that we're not going to get right by this little argument. But let's go a little bit further. This is 1 bit of information that we put in. Let's see how much bigger it makes the black hole. Let's see if we can see how much bigger it makes the black hole. It makes the black hole bigger because when you add energy, you add mass. E equals mc squared. All right, so E equals mc squared. So this can also be written as the change in the mass, let's call it the change in the mass times c squared. The energy that I added goes into increasing the mass, and it changes the mass by this formula here. Let's clean up the formula a little bit. Let's divide by c squared, and that winds up putting the c in the denominator here. That's the change in the mass. That's the minimum change in the mass when you add 1 bit of information is h bar over mg. Okay, let's go a little further. Let's calculate the change in the radius of the black hole. Let's calculate the change in the radius of the black hole. How do I do that? I do it because I know that the radius is proportional to m times g. So I just multiply both sides of this equation. Let's see, yeah, by g. Oh, this was the wavelength downstairs. So we multiply by g. And this is the change in the radius of the black hole. Let's see, where, Did I do that right? The wavelength over the Schwarzschild radius. hc over the Schwarzschild radius is the change in energy. That's delta E. E equals mc squared. So if I want the change in mass, I think I want to divide it by c squared. The change in mass is equal to is equal to h over rc. Agreed? Have I confused you thoroughly? Okay, good. That's the change in mass. And now if I multiply it by g, it gives me the change in radius. This is the change in radius of the black hole. Okay, so every time I throw in one bit of information, I change the radius by an amount which is inverse to the radius itself, with the gh over c. I really think I've lost some c's, but I'm not sure where. Well, maybe not. Where? Oh, you're right. The good. The Schwarzschild radius is not mg, it's mg over c squared. That's where it went. Mg over c squared. So I think this should be by now c cubed, if I'm not mistaken. Is that?
That's where you set everything like c equals 1.
Yeah, don't set c equal 1 in part of the thing and not the other part. Yeah, I think it's gh over rc cubed. That's the change in radius. Now multiply by the radius. R times the change in the radius. What's R times the change in radius? R dr. That's dr squared, right? The change in r squared, apart from a factor of 2, is 2r dr. Just elementary calculus. So r times a small change in r is proportional to the change in the square of the radius. But what's the square of the radius? The square of the radius of the horizon is the area of the horizon. So look what this formula says. It says every time you drop a bit of information in, you change the area of the horizon by a universal amount, which doesn't depend on the mass of the black hole, it doesn't depend on the radius of the black hole at the instant that you did it. You always wind up changing the area by the same amount. It's kind of like saying that every time you drop a drop into a bathtub, assuming the bathtub had nice straight walls, that you always raise the level of the bathtub by the same amount. And it doesn't matter how full it is, you always raise the volume by the same amount. In this case, you increase the area of the black hole by 1 unit, where unit means the area gh over c cubed. Okay. This is a very small area. Every small area is the square of some, or every area is the square of some length, of course. So this is the square of some length. It's the square of the square root. This quantity has units of a length. It's the Planck length. It's called the Planck length. And it's very small. Let's see if we can estimate it. Okay, G in ordinary units means kilograms, meters, seconds. G is about 7 times 10 to the minus 11th. How about Planck's constant? I think, well, that's h bar, I think. Is that h or h bar? 6, I don't remember. Another 7.
H bar is 1054.
Okay. 7 times 10 to the minus 34. That's this. And c cubed, how about c cubed? We have to square, we're going to take the square root in a minute. But what's the square of the speed of light? The cube of the speed of light. Cube of the speed of 27 times 10 to the 24th.
Right.
All right, so we got a 27 times 10, what did I say, 24th? Okay, we got a lot of small numbers upstairs and a lot of big numbers downstairs. This is a very small number. I think it's about 10 to the minus 68th or 69th or something like that. 10 to the minus 69th square meters or something like that. I don't remember exactly. Okay. I happen to remember it's 10 to the minus 66 or 66, somewhere about that, square centimeters.
Minus 68 to 1 and 1 over minus 69.
Okay, the Planck length itself, the square root of this, is about 10 to the minus 35 centimeters. So it's smaller than anything that you can access in any way in experimental physics. And what it says is every time you drop a bit on, the bits, I mean, the way to think about it is the bits are impenetrable and they stick to the horizon. In no finite amount of time do they ever get past the horizon. They stick to the horizon, they have sharp elbows, and they simply push the other ones out of the way, each one occupying about a Planck area.
I have a question. If the first one was sent in and it's approaching the horizon, now the next one comes in and the horizon moves out.
Well, it pushes the other ones out of the way, and it makes the area bigger. And the only way to make the area bigger is to make it bigger.
So it doesn't just increase the radius, and now the prior one is inside. That's
not inside. It's on. No. They never get past the horizon.
Even if you added a huge mass to like two colliding black holes.
Right.
It's hard to believe.
The next one that comes, yeah. That's or we'll go through a bit of that. We have to define what the horizon is in a careful way. We have to define the precise concept of a horizon, which we haven't done yet. We've only,
This may not be probably insignificant, but on the area, what you're saying, a Planck that square is a Planck area on a flat surface, but not necessarily a sphere.
It's a spherical surface.
So it's that's significant.
So for your 8 kilometer diameter black hole, your wavelength that you want for this photon is 8 kilometers.
Right. Long radio. Nice long radio wave.
Like the old barroom trick where if you took a basketball and you wrap a string around it and you add length to it, how far away it is versus basketball, and you do the same thing with the Earth.
Same distance.
You want it the same distance radially.
No, a similar thing. Okay, but that was the magic of that Jacob Bekenstein argued, and in this way argued that the information that you can hide in a black hole is proportional to its area in Planck units. The formula, as it was eventually derived, and I'm going to write it was C equals 1. Maybe I'll try to put the C's in. Wait, let's see. No, I hesitate to try to put the C's in. They go in somewhere, but the entropy or the hidden information in the black hole is equal to the area of the horizon. We think about building up the black hole by dropping in bit after bit. Each time you add 1 unit of area, divide by G, and divide by h bar. I think there's a c cubed upstairs. Yeah, c cubed upstairs. Okay. This means the entropy of a black hole is enormous by comparison with the kinds of entropies in ordinary systems of the same size. You have c cubed, that's a huge number. You have g and h bar, which are tiny numbers in the denominator. the entropy of a black hole is bigger than the entropy of anything else of comparable size by a lot. I mean, anything else that you ordinarily would think about. So huge numbers of bits get stored on the surface of the black hole, proportional to the area, not the volume. So the amount of information you can keep track of in a black hole, or that needs to be kept track of, is less than you might have expected. You might have thought it was the volume of the black hole, but it's still huge. All right, this is probably one of the most important principles of physics. But, yeah.
Was Hawking's formula with S squared?
No, that's fine. Sorry, I missed something. 4. Yeah. Bekenstein had this formula with an unknown coefficient. He tried to estimate the coefficient, and he had all sorts of arguments, but he wound up with peculiar numbers like logarithms of 2 and other things which are not there. It's just 4. It was Hawking who figured out the 4. And good. All right. Well, let's. Oh, there are some interesting. There's one very interesting thing about this formula, and that's that the h bar is in the denominator. What's the meaning of that? Well, you might have thought that entropy, the existence of entropy for a black hole, is a quantum mechanical effect, has something to do with quantum mechanics. And so you might think that the entropy is proportional to Planck's constant, because it's Planck's constant which is the measure of the quantumness of a system. But it goes in the denominator. If Planck's constant were to get smaller and smaller, as it does in classical physics, Planck's constant is 0. It says the entropy is infinite. That's just another way of saying that in classical physics, you can hide, since information is not quantized, it doesn't come in photons, you can put as much information into as small an energy as you like. Take an arbitrarily small amount of energy, you can put as much information onto that a wave, an electromagnetic wave, as you like. But in quantum mechanics, information comes in discrete quanta. The information, or the entropy of the black hole, is finite because of quantum mechanics. It would be infinite in classical physics. You could simply throw arbitrary amounts of information onto that black hole without increasing its mass by almost anything. So this is an interesting fact that although all of this is quantum effect, it's quantum mechanics which prevents the entropy from being too big, not the other way. It makes it finite. What else can we say about this? Well, we could say a lot more about it, and we will. I think I'm getting a little tired, so we'll quit for tonight.
You could say h bar really is angular momentum versus linear momentum. So if you take
well, h bar is simply a constant which has certain units. It has units of angular momentum, it's true, but it comes up in other quantities. It has units of action.
Like this, h over 2 pi, taking regular momentum is very good angular momentum.
No, it's not h over 2 pi that converts it into, no. Angular momentum and momentum differ by a power of a distance. Angular momentum is momentum times distance. Right. Momentum is h over lambda. Lambda is a distance. P times lambda, momentum times distance, has units of h bar. And p times lambda also has units of angular momentum, r cross p. Distance times momentum. Okay. See you next week.
For more, please visit us at stanford.edu.